So A minus is equal to F minus HA. Which is really saying the amount of the base has to equal whatever we started with minus the amount that's in the acid form. And let's put this equation into our Ka value. So we're sort of manipulating Ka now. Come up with a new equation. Now Ka equals H plus times F minus HA over HA. All right, we'll find a way to make this work. So let's cross multiply everything out and start to kind of clean this up a little bit. So Ka times HA everything got cross multiplied. Now we can clean this up a little bit. Just got that cleaned up a little bit. That's what I want to do now. I'm going to bring this part of the equation over here. Now Ka times HA really, I'm just doing some algebra here. Sorry to do that on a Tuesday morning to you. It's Tuesday afternoon, really almost. So those are going to go to that side. And then we're going to look for the common term HA here. So HA, so Ka plus H plus equals H plus times F. Now we have an equation for HA, which is H plus times F over Ka plus H plus. You might say that seems like a lot of work to get to the Ka value, but really, ultimately what it has is a relationship between the pH, the concentration, and the Ka value, which is really kind of what's going on here. Is that the concentration, of course, is relative to the formal concentration, but it's also related to the pH and the pKa's, just like we do here in the term. But if I want to find out what the fraction of the acid is, I want to know how much of the acid is relative to the total amount of acid. So I want to know how much of HA there is relative to HA and A minus. So how many red M&Ms are in the bag as a percentage of all the M&Ms, which you could calculate, of course. So I want to know as a percentage how much of the acid is in HA form versus the combination of those two forms. But remember what HA plus A minus is. This is really just F. So this becomes HA over F. We have an equation for HA. We just made it. Let's use it. So the fraction of HA equals H plus times F over Ka1 plus F, or sorry, plus H plus divided by F. Well, that's good news. We got an F in the numerator and denominator. We can get rid of those. So the formal concentration actually doesn't matter. In the fraction, equation, because really all you need for the fractional equation is the pH and the pKa. So ultimately, this becomes H plus over Ka1 plus H plus. And that becomes the fractional composition equation. So all you need to know is the pH of the solution and the Ka1 to solve for the fraction. The other good news is that the fractions have to add up to 1%. So the other fraction of the acid becomes the fractional composition of A minus. And we can figure out what that is as well. But we don't actually have to do that in this case because the fractions have to add up to 100%. So whatever the first one is, the other one has to be 1 minus that. So if one is 80%, the other one has to be 20%. Honestly, if you want to figure it out the hard way, this becomes Ka1 over Ka1 plus H plus. And when we do a polyprotic system, I'll show you how we actually grind it out for both species. But most of the time, you actually don't have to do that for a monoprotic system because those two numbers are going to add up to 1 anyway. So if you solve for one, you can solve for the other. Let's do a quick example of that. Let's say we have a pH of 4 and a pKa of 5. So let's go back to our little graph here. We're saying that the value here of pKa is 5 and the pH is 4. So it's definitely more acidic than what the pKa would prescribe. And so we're going to have a larger amount of HA than A minus. But actually, let's figure out what those numbers are. So first thing is H plus is 10 to the minus pH, or 10 to the minus 4th. And Ka would be 10 to the pKa, and 1.0 times 10 to the minus 5th. Of course, we just rearranged those equations a little bit. So now we want to solve for the fraction of the acid that's in the protonated form. So the fraction of HA would be H plus is 1.0 times 10 to the minus 4th divided by 1.0 times 10 to the minus 5th plus 1.0 times 10 to the minus 4th by just plugging in the values of Ka and H plus. If you do that, you get a fraction of HA of 0.909, or if you like, about 91%, which kind of makes sense. You're 1 unit away from pKa, so it's about 10 times more acid than base. And then the fraction that's in the deprotonated state would be 1 minus 0.909, which is equal to 9.09, sorry, 0.009. So about 9.1%. And that kind of makes sense again, in that you have about 90%, 91% of the acid is in the protonated state, and about 9% of it is in the deprotonated state. And then all you have to do to get the different values is the Ka values are different, or so the Ka value is the same, but if you just change the pH, you can see how these values change. And if you do this on a plot, for the same system, you can see if you plot the fraction of the acid in the blue line and the fraction of the base in the black line, that if you have pKa equal to pH, like if you did this at pH 5, you can see that they're both at 50%. When you're at 4, this becomes 90% and 10%. And if you go 2 units away, now it's like 99% and 1% of the acid form versus the base form. And then if you flip the script and go to the more basic side, then the base form becomes the predominant one. So if we're doing this at pH 6, then it becomes 90% base, 9% acid, and then as you go more basic, the acidic form basically goes away, and the acidic form goes away, and the basic form goes away. Yep.
I don't know if it's just the angle I'm looking at, but does it seem that the acid can end up being almost 100% versus the base?
You can get, if you go far enough away from pKa, you get to a point where you almost have everything as an acid form and almost no base, and then the same thing happens on the other side of the coin.
But do you see that the blue one looks like it reaches 1, but the black one doesn't?
If you look at it straight on, I think it's closer to both to 1 on both sides, but you are looking at an angle. But yeah, they both can get to about 1. And then you can kind of see when I was talking before about when buffers are good, is that buffers are really only good in this little range here, kind of I'd say from about 0.8 or so to 0.2, where you have a little bit of both species. Of course, the best buffer is when you have 50-50 of both. And this is really why buffers are no good outside of about 1 unit anyway. Because outside of 1 unit, you have a lot of one and not much of the other. And then on the other side of the coin, you also have a lot of one and not much of the other either. So this is kind of the sweet spot of the base, is right in the middle here when you have a little bit of both sides of the coin. All right, so that's a good place to stop. We'll talk about the diacritic system and we'll do some test prep on Thursday.